Now, this example is a little different from previous ones, since we're not talking about the limit at a number. We're talking about a limit at infinity. So what we're asking here is what happens to the function as the values of x get really large. So to see what the behavior is, let's try looking at some specific values. If we start with x equals 10, then the function equals 1/10 or 0.1. Now, we're interested in what happens as x gets really large. So let's jump from there up to x equals 1,000. This makes the function 1/1000th or 0.001. And so let's try one more. Say we let x equal 1 million. Then the function is 1 over 1 million or 0.000001. So hopefully at this point you can see the trend, right? That's what we've always been talking about when we talk about limits. As the x values get larger and larger, the function values get smaller and smaller. That is closer and closer to 0. So that's going to be our limit. Now, another way to approach the problem is to look at the graph. The graph of f of x, right, f of x equals 1 over x, looks like this, with a horizontal asymptote here at y equals 0. So in other words, the function gets arbitrarily close to x as x gets large, but never actually gets there. So this kind of supports our conclusion that the limit is 0. Now, a word of warning about graphs, right? Looking at graphs can be informative, but because any drawing is going to be inherently inaccurate, I would never stop there. Once you think you know what the limit is based on the graph, you still have to go back and give an algebraic argument for why that result is the right one. So here we have another limit at infinity situation, but where the function, is more complicated. So to see what's happening here, I'm going to take the unusual step of dividing the top and bottom by x squared. When I do that, watch what happens. This is the new top part, and this is the new bottom part. Now, at first, the expression just seems to get messier, right? But when I start reducing all of these individual terms, things get more interesting. Now, you see, now I can apply our limit rules, right? We have the limit of a fraction, which means that I can just take the limit of the top and the limit of the bottom. And then I can go further and just take the limit of each piece. So this whole limit becomes that's the top. Then the bottom is this. Now, each of these individual limits. Think back to what we did on the previous slide. The limit as x approaches infinity of something over x is 0. And similarly, right, if 1 over x is going to 0 as x goes to infinity, then something over x squared is even bigger than x, so this is also going to 0, and it's doing it even faster. And these last limits, now you want to think all the way back, right, a couple lectures back, the limit as x goes to something of a number is just the number. So if we put all of this back together now, the top is 1 plus 0 plus 0, and the bottom is 3 plus 0 plus 0. So the limit is 1/3. There's our final answer. So I want you to think for a second, right? Think about this as a technique that we can use. When we want to take the limit as x goes to infinity of a rational expression, which is what we started with here, we can figure that out by dividing the top and bottom by x to the biggest power, right? And then we're going to get all this great cancellation, and we're going to end up being able to get our final answer. So let's look at another one here. Right? Look at this thing. And I'm going to use the same technique. Right? I'm going to divide the top and bottom by x to the 4th. Right? That's the biggest exponent. And I'm going to do the same thing to the top and the bottom. Don't try to do the top by x to the 4th and the bottom by x to the 3rd, right? Remember, I can do whatever I want to this fraction as long as I do the same thing. I can multiply or divide the fraction as long as I do the same thing to both the top and the bottom, right? So, now watch what happens to the limit, right? This becomes the limit as x approaches infinity. I want you to think about, right, distributing this x to the 4th into here. This becomes 5 over x to the 4th, which is 5, plus 3x squared over x to the 4th, which is 3 over x squared, minus 1 over x to the 4th. And on the bottom, 2x cubed over x to the 4th is 2 over x. 4x over x to the 4th is 4 over x cubed. And then finally, just this 2 over x to the 4th. All right, so now limit rules, right? I can take the limit of each of the individual terms in the top and bottom. This one is 0. This one is 0. And in fact, all three on the bottom are 0. So the limit becomes 5 plus 0 plus 0 over 0 plus 0 plus 0. And you see, now we're in trouble, right? This became 5 over 0, which is undefined. All right, so now you got to ask yourself real quick, right? Think back to the original expression of there. Think, is there anything I can factor or cancel out? I don't think you're going to be able to in this case. So when this happens, right, remember, this is sometimes what our answer is going to be. In this case, our answer is the limit doesn't exist. And sometimes that's going to be where we end up. All right, so now here, I want to kind of switch directions a little bit, talk about piecewise defined functions. And with a piecewise defined function, we have an additional concern. We need to be concerned about the point where the function transitions from one formula to another. In this case, that's at x equals 2. At x equals 4, the first limit here, we're squarely in this x greater than 2 range, right? So in this area, the function is well behaved. It's a line. So that makes the limit as x approaches 4 of f of x just 4 minus 1, which is 3. All right, that's kind of the easy part, right? So for x equals 2, for the limit at this transition point, we have to really kind of apply our definition and look at the function from both sides. From the right, that's going to be the limit as x approaches 2 from the right. Or we're talking about values greater than 2, so we're going to need to use the x minus 1 function. That makes this limit 2 minus 1, which is 1. Okay. Now we need to come at it from the other side. The limit of f of x as x approaches 2 from the left. Well, on the left-hand side, we're talking about numbers that are less than 2. And to the left of 2, this is the formula that we use. So the limit here is going to be 2 squared minus 3. That's 4 minus 3, which is 1. The limits match, right? Because the limit as x approaches 2 from the left is the same as the limit as x approaches 2 from the right. We can conclude that the limit as x approaches 2 of f of x is 1. All right, so how about this one? Right, we're talking about the limit as x approaches negative 1. And you see that's the transition point, right? So when you're doing it, when you're looking at a piecewise defined function, and you want to know the limit as x approaches that transition, all right, then you have to look at the limit from each side. The limit of f of x as x approaches 1 from the right, that's this part, right? Numbers greater than negative 1, equals 3 times negative 1 squared plus 1. That's going to be what? 3 plus 1, which is 4. Now we'll do it again. The limit of f of x as x approaches 1 from the left. Now we're down here on this side, right? To the left of negative 1. So we're going to use this formula. It's going to be negative 1 to the third minus 3. That's what negative 1 minus 3, that's negative 4. And the two values are not the same. Right? We got different results. Therefore, this is an example of a situation where our conclusion would be that the limit does not exist.